Okay, let's unpack this. Today, we're diving deep into a topic that sits squarely at the intersection of waste, valuable resources, and, well, the often complex reality of making things truly circular.
Hmm.
We're talking about recovering carbon black from those mountains of old tires that reach the end of their road.
Yeah, huge issue.
The tire industry needs tons of carbon black, traditionally made from oil, a non-renewable resource. The potential to get this material back out of used tires seems huge,
It's
right?
absolutely huge potential.
But spoiler alert, getting it out cleanly and making it high quality isn't quite as simple or as environmentally friendly as you might initially hope.
No, it's a fascinating challenge because tires are just this massive global waste stream. And the materials locked inside, well, they represent a significant draw on virgin fossil resources.
Right.
So figuring out genuinely sustainable ways to handle end-of-life tires and make those materials circular is absolutely critical.
Absolutely. And we've got some really sharp thinking to guide us today. We're pulling insights from a detailed new research paper just published by a team at the University of Aveiro, Portugal.
Mhm.
They use this deep dive environmental assessment called consequential life cycle assessment.
Right, the specific kind of LCA.
Plus, we're getting a dose of fresh, real world perspective from a leading consultant in the field, shared in their June 2025 newsletter.
Yeah, that industry viewpoint is crucial.
So, our mission in this deep dive is to cut through the complexity, understand the environmental consequences of different ways to recover this carbon black, see what the science tells us about the maybe uncomfortable trade-offs between quality and sustainability,
Yeah, those trade-offs are key.
and then stack that up against what the industry sees as practical and achievable right now.
It's the perfect combination, I think. Rigorous science and, practical industry insight.
Couldn't agree more. So let's ground ourselves in the scale of the problem first, pulling from the research paper. They hit you right away with the fact that global resource extraction is just, well, skyrocketing.
It really is.
Material demand hit an eye-watering 12.2 tons per person back in 2020. That's our global material footprint just getting heavier and heavier.
And despite the growing focus on the circular economy aiming to dramatically reduce that resource consumption, the paper points out something quite stark. Progress is slow.
How slow?
Well, the global circularity rate was only 7.2% in 2023, and worse still, it's actually down from 9.1% in 2018.
Wow, down.
Yeah, globally, we're actually sliding backward on circularity, which is not great.
That makes the need for solutions in major industries like the tire industry even more urgent. As the paper notes, it's highly dependent on non-renewable resources like oil for key materials, especially carbon black.
Exactly. And when millions of tires hit the end of their life,
Wow.
they become waste.
A massive amount of waste.
Waste that often still ends up in landfills and vast stockpiles, despite regulations. You see this even in places like the EU, which banned landfilling end-of-life tires way back in 2003.
Right.
So finding ways to unlock the value in those tires, as the paper discusses, isn't just, green thinking. It's a practical necessity.
So aside from retreading, which I guess isn't always possible,
No, not always.
what are the typical fates of these tires? The paper outlines a couple of main paths. Material recovery, that's separating the rubber, steel, textiles,
Yep.
and energy recovery, which is basically burning them for fuel.
Right. Material recovery gives you things like recycled rubber crumb, which you see in asphalt or playground surfaces.
Okay.
But the paper does flag a point sometimes raised about potential health concerns from volatile organic compounds, VOCs, in some of those uses.
Okay.
And energy recovery, like incineration, is generally the less preferred environmental option. The paper explains this is due to pretty significant negative environmental impacts, and crucially because you just destroy valuable raw materials that could otherwise be recovered.
And that is where a technology called pyrolysis enters the picture as a promising alternative. How does the paper describe this?
So pyrolysis involves heating tires in the absence of oxygen. This thermal decomposition allows you to recover valuable materials. You get syngas, tire pyrolysis oil, TPO, and what we're really focused on today, recovered carbon black, or RCB.
What kind of yields are typical, like percentages?
You typically see over 40% TPO, up to 40% RCB, and then maybe around 20% gas.
Okay.
And the syngas is often smartly used to actually power the pyrolysis process itself, which helps cut down on external energy needs.
That makes sense. So The big idea, the potential value here, is that RCB could potentially replace traditional fossil fuel-based carbon black in things like paints, plastics, and yes, even new tires,
Hmm.
offering environmental savings. And the TPO can stand in for fuel oil.
Exactly. And the research paper we're diving into really hones in on the process specifically designed to produce high-quality reinforcing RCB HQR-RCB.
High quality, okay.
Yeah, they're aiming to replicate the properties of a common high-performance traditional grade, the N300 carbon black.
Let's walk through the specific pathway they studied for creating this high-quality stuff. It starts with tire rubber crumb, which, has to be transported, adding an initial environmental footprint.
Right, transport's always a factor.
Then comes the core pyrolysis step itself, heating that crumb to 550 degrees Celsius without any oxygen around.
That gives you the raw RCB. But as the paper details, this initial product isn't really ready for prime time and demanding applications like new tire treads.
Why not? What's in it?
Well, it's got inorganic additives, fillers, traces of steel maybe, and carbonaceous residues left over from the process. So initially, its properties are closer to semi-reinforcing grades, not that high-performance N300 they're aiming for.
So to get that higher quality, you need post-processing steps. And the paper identifies a few key ones. The first, and perhaps most significant, being demineralization.
This is the big one if you're chasing high quality.
Mm-hmm.
You need to slash that inorganic ash content way down below 2%.
Okay.
And this requires sequential treatment with strong acids, like nitric acid, in the paper's main scenario, followed by strong bases, like sodium hydroxide.
Sounds intensive.
It is. It's an intensive step, demanding substantial inputs of these chemicals, plus water and natural gas for heating and drying the material afterward.
Okay, so demineralization is one step. And then there's activation.
Right. A steam activation process cranking up the heat even higher to 750 degrees Celsius. The idea is to clean the RCB surface and boost its performance characteristics.
And more energy needed there, too.
Yep, this also needs natural gas for heat and to produce the steam itself.
And finally, milling and pelletization to get the product in the right usable form, like little pellets.
Precisely. These finishing steps require electricity, a binder that used lignosulfonate to hold the pellets together, and again, more natural gas for drying the pellets.
Gotcha.
And for their LCA, the paper based everything on producing just 1 ton of this finished HQR-RCB.
Just 1 ton as the unit.
Yeah, and they model the environmental credit they get by saying this ton substitutes 1 ton of new carbon black and about 1.48 tons of non-refined fuel oil, which is what the TPO output is assumed to replace.
Okay, so they've got the whole process mapped out, inputs, outputs, substitutions, everything. They run it through this rigorous environmental assessment, the life cycle assessment. What does the base scenario making the HQR-RCB with all those post-processing steps tell us?
Okay, here's where it gets really interesting and perhaps a little surprising for some. The paper finds there are indeed net environmental savings.
Okay, good news.
But only in 2 specific areas: resource use for fossils and resource use for minerals and metals.
Only 2.
Yeah. Essentially, the benefit of not having to extract virgin materials outweighs the impacts of the recovery process just in those 2 categories.
But that leaves how many other categories?
7 others. In 7 other crucial environmental impact categories, we're talking climate change, ecotoxicity to ecosystems, nutrient pollution or eutrophication, acidification, smog formation, particulate matter, and human toxicity.
Wow, okay.
In all those areas, the process still results in significant net environmental impacts. So the good news on resource depletion doesn't cancel out the bad news on pollution and ecosystem health in these other areas.
That's a critical nuance, isn't it? Just because it saves some resources doesn't mean it's good overall.
Yeah.
And where is the main culprit behind those impacts? Where's the hotspot?
The paper points the finger directly at the demineralization process. It's the primary environmental hotspot.
The acid and base washing part.
Exactly. It's responsible for a huge slice, somewhere between 51% and 90% of the total gross impacts across those sensitive categories. It's mainly the production and use of those strong chemicals, the nitric acid and sodium hydroxide, that dominate the environmental burden. Other steps like milling, pelletization, the binder use, and activation with natural gas, they contribute too. But demineralization is the clear leader in negative impacts.
So the very step required to make the RCB high quality is its biggest environmental drawback. That's quite the trade-off. Did the paper explore ways to mitigate this, maybe make it cleaner?
They did. They ran a scenario analysis testing some alternatives. For instance, swapping out natural gas for biomass, for heating.
How did that work out?
It helped a bit with climate change and fossil resource use, as you'd expect, but it actually slightly worsened impacts in some other categories, so not really a silver bullet.
Okay. What about using different chemicals for demineralization? They use nitric acid first, right?
Right. They tested acetic acid and hydrochloric acid instead. Acetic acid was a definite step backward, significantly worsened the environmental profile of most categories.
Oh, okay, worse.
But hydrochloric acid, or HCl, however, was much better. It significantly improved the profile across 8 out of the 9 categories compared to nitric acid.
8 out of 9, that's substantial.
Yeah, leading to notable impact reductions, up to 75% in some cases.
Okay, so that sounds like a promising option. Then maybe that's the way to make high-quality RCB work.
Well, it's less bad, yes.
Yeah.
Definitely an improvement. But here's the paper's key finding. Even with hydrochloric acid, net environmental impacts still remained in 7 out of the 9 categories.
Still 7.
Still 7, just like the base scenario, but at a reduced level. So you make the process cleaner, you reduce the impacts, but you don't actually flip the overall balance to a net environmental benefit in most categories.
That's a really powerful finding. So cleaner demineralization helps, but doesn't solve the fundamental problem for most impact areas. What scenario did show the most dramatic environmental shift then?
The most eye-opening comparison, I think, was looking at a scenario that skipped the post-treatment steps entirely.
Just pyrolysis and basic finishing.
Exactly. Specifically, they looked at the RCBA-A scenario, which only involved pyrolysis, milling, and pelletization. This produces lower quality RCB, obviously,
Yeah.
something closer to non-reinforcing or semi-reinforcing grades, maybe like the N660 grade mentioned in other studies you might see.
Okay, so simpler product, simpler process, and the environmental outcome for that.
Dramatic.
Yeah.
Just completely different. This scenario achieved net avoided burdens. So net environmental benefits in 8 out of the 9 impact categories.
8 out of 9. It flipped completely.
It completely flipped.
Yep.
Instead of having net impacts in most categories, it showed net environmental benefits across almost the entire spectrum analyzed.
Wow. Okay. So the paper's core message here seems pretty clear then.
It's stark, really. The environmental impacts are directly proportional to the target RCB quality, at least via this pathway. Trying to hit those high reinforcement properties through complex post-processing, especially that demineralization step, creates a negative environmental profile in most areas. Whereas producing a simpler, lower quality RCB that avoids those intensive steps is dramatically more environmentally beneficial across the board. There is a clear, quantifiable trade-off between quality and sustainability in this specific recovery pathway.
That scientific finding leads us perfectly to the industry perspective from that newsletter. How does someone on the ground dealing with the practicalities of bringing this stuff to market view these findings? Does it resonate?
It really does. The industry expert writing in the newsletter pretty much echoes the paper's main points. They agree that RCB production involves these environmental trade-offs, and those post-processing steps, especially demineralization and activation, do carry significant environmental burdens.
And their specific take on that demineralization step, which they might call ash-leaching.
Yeah, ash-leaching. Their advice is pretty blunt. They recommend against ash-leaching for now.
Against it. Why? Just the environmental reasons.
Well, they cite the LCA reasons from the paper. The environmental cost is high. But they also add crucial practical concerns, like handling the massive volumes of strong acids needed.
How massive?
The expert mentions roughly 10 times the volume of the RCB itself. Handling that creates major process safety headaches.
Yeah, I can imagine.
And the cost. Both to build the facility for it, the CapEx, and to run it, the OpEx, it's substantial.
So it's not just environmentally costly, it's economically and operationally costly and potentially risky too.
Exactly. And the expert adds another point. Even after all that effort and expense with leaching, the resulting product is still a complex mixture of different carbon blacks. It's not like you get one pure grade out.
Okay.
So their conclusion is that it's simply a more straightforward and frankly less risky path for producers to first commercialize a stable, consistent RCB product without the leaching step. Focus on getting that right first.
That makes a lot of sense, aligning the environmental findings with the practical challenges. What about the industry's focus then? Do they have to chase that N300 equivalent, the absolute highest quality RCB, for it to be useful?
This is another point where the industry expert offers a really useful, practical perspective. They note that while tire treads are, a high-value application, the picture is shifting a bit.
How so?
Well, car tire treads in Europe, for instance, are increasingly using silica-silane systems for performance, not just relying solely on carbon black.
Ah, so the demand for the highest end carbon black in that specific application might be changing anyway.
It might be. And the expert argues that the market for less reinforcing grades, think N700 and N600 equivalents, is absolutely enormous already.
How big?
We're talking millions of tons per year globally. This represents what the expert calls an ample playing ground for RCB producers,
Okay.
especially for those who might not be able to hit the very top-tier performance needed for the most demanding applications like, say, high-performance tire treads, at least not without that problematic post-processing.
And isn't there another angle here? Can't you make high-quality reinforcing carbon black from the TPO output anyway, the oil fraction?
Yes, that's a critical detail the expert highlights. You can take the tire pyrolysis oil, one of the main products from the pyrolysis process alongside the RTB, and actually use existing established technology to produce truly highly reinforcing prime carbon blacks from it.
Ah, so the industry doesn't necessarily need the RCB itself to hit the highest performance targets. They can use a different output from the same initial tire pyrolysis process for that goal.
Exactly, which kind of bolsters the expert's recommendation. Focus RCB efforts on what's currently achievable and marketable without the complex, costly, and environmentally burdensome post-processing.
Right.
Target those large market segments that need decent quality carbon black, maybe like those N600 and 700 types, but not necessarily the absolute highest reinforcement properties that come with such a high environmental and economic cost.
This brings us to the expert's second major point, which sounds like a bit of a dose of reality for aspiring producers. The question, can you actually sell our RCB? It sounds like it's not a simple case of build it and they will come.
No, it's definitely not a walk in the park. The expert notes that many hopeful producers often don't have what they'd call a truly engineered product yet, meaning it might just be what they call a black char, just the basic output from the pyrolysis reactor. And these producers often mistakenly assume they can just sell it like a standard commodity, maybe even before their facility is fully built and running consistently.
What goes wrong there? Why isn't it working?
Well, the expert lists common pitfalls they see all the time. The feedstock, the old tires going in, isn't controlled for consistency.
Okay.
The pyrolysis process itself isn't optimized to yield high-quality, consistent RCB. The material isn't sufficiently milled to the right particle size. It's often not pelletized, which customers usually need for handling.
Right. Logistics matter.
Yeah, and there's no consistent quality control after production. And crucially, often no real application development has been done to show customers how to use it effectively. They describe it as frequently being a poker play, just hoping it all works out in the market.
So why isn't RCB a commodity like traditional prime carbon black? Why can't you just sell it easily?
This is really key, because currently, there are very few established industry standards and classifications for RCB. It's not like virgin carbon black where everyone knows what an N330 or an N660 is.
Ah, okay.
This means specifications often have to be custom-tailored and agreed upon with each potential customer. That makes it much more of a make-to-order business model.
I see.
It's far more service-intensive and complex than selling a standardized, globally recognized commodity where the specs are known and trusted.
The expert mentions a successful pre-contract example, Infiniteria Enviro, in the newsletter. What makes their approach different, according to the expert?
Well, the newsletter highlights that this isn't a new effort for them. They apparently started application development decades ago.
Decades. Wow.
Yeah, that long history builds confidence.
Yeah.
Plus, having strong financial partners, like Anton and Michelin in their case, lends credibility. It assures potential customers that the company has the backing to ensure long-term, consistent supply.
Which is vital, right? If you're a manufacturer incorporating new material into your products, you need to know it'll be there next year and the year after.
Exactly. You need that reliability.
So it's less about just making the product and more about the long game of marketing RCB, proving its value, its consistency, and its reliability to customers over time.
Precisely. It requires a lot more effort in partnership building, trust building, and technical support at this stage compared to selling a mature material that has decades of standardized specifications and established supply chains behind it.
Before we wrap up, the industry newsletter had a really interesting little side note, almost like a postscript at the end.
Yeah, that was cool. A mention of RCB being successfully used in agriculture, specifically helping grow lettuce.
Lettuce, agriculture, that's completely outside the tire or rubber world.
It is, and the expert highlighted it as just a neat example of finding valuable, maybe unexpected applications for RCB outside its traditional markets, Which, interestingly, the research paper also touched on in its future perspectives section, the idea of looking beyond typical rubber applications.
Fascinating. Okay, let's try and pull all these threads together then, from the detailed research paper and the pragmatic industry expert. What's the big synthesis here? What are we learning?
Well, the research paper delivers a clear, quantitative message. Improving RCB quality by adding complex post-processing steps, particularly that demineralization, comes at a significant environmental cost across most impact categories. It's measurable.
Right.
Conversely, producing a simpler, lower-quality RCB without those intensive steps has a dramatically better environmental footprint overall. The trade-off is real.
And the industry expert's practical advice lines up perfectly with that scientific finding, doesn't it?
Absolutely. Their recommendation is basically avoid the costly, complex, and environmentally intensive ash leaching process for now. Don't chase the absolute peak quality if the cost is too high in multiple senses. Instead, the focus should be on consistently producing a good quality RCB without it, and targeting the huge existing market segments, like those N600, N700 equivalents, which don't demand the highest possible level of reinforcement. Go for the volume market, where the environmental profile looks much better.
So the big takeaway isn't just about technical circularity, closing the loop on materials, but about genuine environmental sustainability.
Exactly. The paper stresses that simply recovering a material isn't automatically an environmental win. True sustainability requires optimizing the process itself, perhaps finding ways to recirculate those harsh chemicals in the future, as the paper suggests, or developing entirely new, more sustainable materials and applications altogether.
And both sources kind of acknowledge the field is still maturing, right? There are limitations.
Yeah, definitely. Things like data availability for LCAs are still improving, and there's a real need, the expert points out, for clearer industry terminology and classification for RCB as more real-world production data emerges. It's still early days in some ways.
So what does this all mean for us, thinking about this? This deep dive into recovering carbon black from tires, guided by solid research and that dose of industry reality, teaches us a really critical lesson, I think.
Hmm.
Simply calling something circular doesn't automatically mean it's better for the environment across the board. Chasing the absolute highest quality material, at least with the current technology studied here, comes with a significant environmental price tag.
Yeah, due to those intensive post-processing steps like demineralization.
There's a quantifiable trade-off here between maximizing material performance for the most demanding uses and minimizing the overall environmental impact. It seems the more complex you make the process to refine the material,
The higher the environmental cost seems to climb in many categories.
it truly highlights that circularity is a necessary goal, but maybe it's not the whole story. We have to look at the pathway to circularity and ensure those pathways are genuinely sustainable themselves.
Well said. The how matters as much as the what.
It raises an important question for you, the listener, to consider as you look at the whole circular economy push. Where should the primary focus really lie? Is it always about perfectly replicating the highest quality virgin materials, even if that demands environmentally burdensome processes?
Good.
Or is it perhaps more impactful to find the most environmentally beneficial pathways for recovered materials, maybe targeting applications where a slightly different performance is perfectly acceptable, or even finding entirely new uses outside the material's original life, like that lettuce example?
It's a complex balance, isn't it? There's no single easy answer.
No, but understanding these specific trade-offs, like the one we saw today between RCB quality and environmental impact, feels absolutely key to making truly sustainable choices as we move forward. Something to definitely keep thinking about.